Okay, so this is a lecture, full-length lecture, I guess a class lecture on building an MCMC for this bladder cancer data set. I've titled here Metropolis-within-Gibbs. You've read now, and we've talked, or you've seen videos maybe on doing Gibbs and doing Metropolis. The idea here is that you're going to build a Gibbs sampler, but some of the steps you can't sample directly from, and so you're going to use a Metropolis for that step. And so that's what we're going to see today. Since this is a little bit longer, I just had an outline here about what we're going to do. I'm just going to briefly mention this whole idea about doing Metropolis-within-Gibbs, and then I'm going to remind you what that bladder cancer model was, that hierarchical model that we were using for that data set, and describe what the Gibbs steps would be and derive those. And then I'm going to turn around and look at a graphical model representation of this hierarchical model, right? And how we can use that to think about conditional independence in our Gibbs sampler. I'm going to then fully define our full MCMC algorithm. I'll tell you what exactly MCMC means at that point. And then we're going to go through looking at convergence. Right? So at the end, we're going to talk about using JAGs, which we've done before. But what we haven't even tried to do before is to look at convergence of our MCMC in JAGs. Right? So basically, the idea here today is to just go through this bladder cancer hierarchical model and write up our own Gibbs sampler or our own MCMC algorithm to sample from the posterior. All right, so previously we've talked about, or at least there have been videos and you've read about the Metropolis-Hastings algorithm and the Gibbs sampling algorithm. All right, and they've been presented, at least initially, as two completely distinct approaches. They are both Markov chains, and it turns out that you can actually combine them into an analysis. Hence, the idea here is that, all right, Gibbs sampling says that we can sample from all the full conditionals. Right, so we break up our big parameter vector theta. We're trying to draw from some posterior for this big vector theta. And we're going to break it down into components indexed by k. Right, here from 1 up to capital K. And the Gibbs sampler says, all right, imagine that you can sample from the full conditional for theta k, where the theta negative k indicates the entire vector theta except without the component k. Right, so imagine that you could actually sample from all of these full conditionals. All right, great. If you can run the Gibbs sample on its own. But what if you can't? Right? What if you can? Well, what if you can't sample from all of them? Right? Maybe you can sample from some of them, or maybe you can't sample from any of them. Right? Then what do you do? Well, it turns out that what you can do is just substitute, instead of having a Gibbs sampling step for the full conditional for theta k, just sub in a Metropolis-Hastings step. Right, so that's the whole idea of doing Metropolis within Gibbs. So imagine here that, right, you can do these full conditionals for all k except for a single one of them. Right, so you do Gibbs sampling steps for all but one. For that one step, you substitute a Metropolis-Hastings step. Right, and it turns out that all the convergence results that we have still hold for this situation. Right, so we still know that the sequence of theta draws that you have converge to the target distribution, that is the joint distribution for all the thetas. We still have a law of large numbers. When the central limit theorem applies, we still have the central limit theorem, so forth. So all the results that held for Gibbs sampling Metropolis-Hastings still hold when you substitute some of the Gibbs steps for Metropolis steps. Okay. All right, ready to see an example? All right, so here's this bladder cancer data set. Remember that this bladder cancer data set is, for what I used, the years 2000, 2004. For each county in the U.S., it had the number of deaths associated with bladder cancer, and then it had also this quantity of the number of person years during that time period. And I guess the data set I actually have been using is just for white males. All right, so the y sub k is going to be the number of deaths we actually observed in county k over that time period. N sub k is going to be this person years in that county divided by 100,000. And this is the parameter that we're really interested in, is the expected deaths per 100,000 person years in each county. Right, and so previously we modeled the data as being conditional on those expected deaths or independent Poisson distributions, with a mean that depends on the number of person years times the expected death for those person years. And then we put a prior on the expected death rate in the counties that has a gamma distribution. We use this because it was conjugate, and we'll see where that comes up in a second. And if we had stopped here and plugged in values for alpha and beta, we would have had a standard Bayesian model. But we're going to do this as a hierarchical model, so we're going to put priors on alpha and beta and therefore learn what alpha and beta are. In this case, we have such a large data set that I just chose uniform priors for alpha and beta. For some values, alpha A naught and B naught, we're here, just to be explicit, alpha and beta are independent. All right. Everybody remembers that model? Yeah. Or at least models that are very similar? Okay, so now the question is, what we'd like to do is, well, ideally, we would have an analytical form for the posterior distribution. The posterior distribution here is this distribution. Right, so for the vector theta, so this is the theta for all of the counties put into one, and alpha and beta, so the distribution for theta, alpha, and beta, conditional on y, the posterior distribution for parameters theta, alpha, and beta. We'd like to have an analytical form. We talked already about we don't have an analytical form for that. Previously, we've talked about how you could get the marginal distribution for alpha and beta, and then sample conditional on that, sample thetas conditional on those alpha and betas. Here we're going to use a Markov chain Monte Carlo approach. All right, so the first thing to do is to take this posterior that we're interested in and write down what it actually is, at least up to a proportionality constant. Right, it's proportional to the likelihood. Likelihood here, right, is the piece here of this is the Poisson probability mass function for the number of deaths that we have observed, which is dependent on the expected death rate and the number of person years. And then we have the product over all the different counties. Then we have the part that's the hierarchical, well, the prior for the different counties. This is now each county, what we assume that it was gamma with parameters alpha and beta, and then times the prior for alpha and beta. Good. Okay, so that's what we have. Now, here, we've just plugged in the forms for those probability mass and probability density functions. Right? And we've gotten rid of anything that doesn't involve the quantities that are left of the conditioning bar. Right? So anything that doesn't involve theta, alpha, or beta. So in particular, the first term here, right, should look like the probability mass function for a Poisson with an observation yk and a parameter nk theta k. Right, you'll notice that there's no yk factorial in the denominator, because yk doesn't have a theta, alpha, or beta in it, so that just gets swept up into the proportionality constant. It doesn't have an nk raised to the yk. Right? This piece right here should be nk theta k all raised to the yk, but nk to the theta, yk doesn't have a theta, alpha, or beta in it. So that can all just be dropped. The next piece we have is the prior for all of the different expected death rates. And the easiest thing to forget when writing this down is this term right here. Right? This normalizing constant for this prior for the expected death rate. Right? Oftentimes we can get rid of the normalizing constant, but because the normalizing constant involves alpha and beta, which is of interest here, we cannot just drop it. Okay. All right, so here's the gamma prior for theta k, and then we have the two uniform priors for alpha and beta. All right, so that right there is our target distribution. So the goal here is to sample from that target distribution. Any questions so far? Okay, so the key now is going to be we're going to think about using a Gibbs sampling approach. Right, Gibbs sampling is probably the easiest thing to do, so go ahead and try it first. All right, so in order to find Gibbs samplings, we need, I'm going to derive now the different full conditionals that we would need. All right, so first here is the full conditional for the expected death rate of county K. The full conditional part means that we're going to condition on everything else that's in the model. So we're conditioning on the data, we're conditioning on all the other thetas. Right? That's why we have theta minus k. And we're conditioning on alpha and beta. And the way to start out deriving this full conditional is to make it proportional to the target distribution of interest. Right? And now what we're going to do is we're just going to write down what that target distribution of interest is, which is above. But we're going to drop out any terms that now do not involve a theta k. Right? So any term that doesn't involve theta k is just going to get dropped. That ends up being a whole lot of terms. Notice that here in this product, right, in the product, the only one that we care about is the product over k. Not the product over k, is the term for k. All those other terms involve a theta 1 or a theta 2 or a theta 3 or a theta capital K, but don't involve the k that we're interested in. So all of that just gets swept up into the proportionality constant. Okay? We don't care at all about the prior or any components that only involve alpha and beta, because all we care about now is those that involve theta k. So you notice here that the normalizing constant for the gamma disappeared. These indicator functions all disappeared. Okay, so fine. So we've gotten rid of anything that doesn't involve theta k. And now we have some terms that we can combine. Right? We have theta k raised to some power. So we can add those powers. We have e to the something that involves theta k's. Right? So we can add those two exponents and combine the terms. All right. So now the key is you need to recognize that as the kernel of some distribution.
Gamma?
Yes, it's a gamma. Did you know that from the kernel, or did you know that from other?
Vaguely. It was a yes. Is that a gamma or beta?
So the thing to remember here is that we intentionally used the gamma prior for theta k because it's conjugate. Right? So because it's conjugate, we should have known immediately that the posterior is also going to be a gamma. In this case, the full conditional here is going to be a gamma. All right, so that's fine. So this turns out to be proportional to the gamma distribution with those parameters. All right, so one thing to note here is that this gamma distribution doesn't depend on any of the other theta k's. Right? It doesn't depend on any of the other expected death rates for any of the other counties. It doesn't depend on any data other than the data for county K. Right, so right here, when we have the full conditional for theta K, and we've made it explicitly conditional on all of the data and all the other expected death rates in those counties, well, that's not actually true. Right? It's conditionally independent. So conditional on alpha and beta, and conditional on the observation from county K. It's conditionally independent of all the other expected death rates in all the other data. That's what we've shown right here. Yes?
Why were you able to drop the product?
Right, so it might be helpful. So the question is, why was I able to drop the product? And the thing to think about is, all right, maybe imagine these all in a line, right? So you have the theta 1 terms here. So you have e to the negative n1 theta 1 to the y1, and so forth. Well, none of that involves the term theta k. Right? All I'm interested in about is the term that involves theta k. So since that term doesn't involve any theta k, it just gets swept up into the proportionality constant. Other questions? So we've done now the vast majority of the full conditionals we need. Right? There are capital K counties here. We've done all of those so far. All we need now are alpha and beta. All right, so let's do the full conditional for alpha. So again, what we do, so full conditional now depends on all the data, all the expected death rates, all of, the parameter beta. we might write it as proportional to the target distribution that's of interest. And now we're going to do the same thing. We're going to write it down, except we're going to get rid of everything that doesn't involve an alpha. All right, so yeah, okay. So, right, none of this involves an alpha. This doesn't involve an alpha. The indicator function there doesn't involve an alpha. So this is what we have. We can maybe simplify it a little bit to get that. All right. So this is the kernel of what distribution? Unknown, yes. I don't know what it is. Right? Yeah. It's not the kernel of any known distribution. Yep.
It should be beta.
Oh, beta n, yes. Thank you. It should be, yes, this should be a capital K. The n, beta to the n should be a beta to the capital K. Thanks. Yeah, I did it all from I equal 1 up to n, and then I changed it all from k equal 1 up to capital K, and missed one. Yep, see more capital K's here in the product sign. Absolutely. Thanks. I will fix those. All right, so yes, so if we replace these n's with capital K's, yes. Right, so this minus 1, you could have written this theta k as theta k to the alpha over theta k. Right? That theta k now doesn't have an alpha in it, so that just gets swept up into the proportionality constant. All right, so the point here is that, all right, if we would like to do Gibbs sampling, pure Gibbs sampling, we're stuck. Right? This is not a distribution that we know how to sample from. So this right here is where we're going to put a Metropolis-Hastings step into our algorithm. Yep.
I didn't ask this before because I didn't understand, but now I kind of understand. About the full condition of the theta k,
yep.
You arrive to the conclusion that the posterior does not depend on all the thetas that are not k's. You arrive to the conclusion that
the full conditional.
The full condition is independent of.
Yes.
Okay. But that is because you assume the prior is gamma. I mean, that's an implication of your model, not because the data actually is independent.
So, okay, so just to reiterate the question for those maybe listening online, the question here is about the full conditionals for theta k being independent of all of other theta k's, right? And the question was about when does this occur, and your statement is that it only occurs because I assume that they're gammas. It's true because I assume that they're independent in the prior, not because I assume that they're gammas. Right? Yes. So for any distribution that I would have assumed for the theta k, as long as I assume that they're independent in the prior, then I would have had the result that they're independent in this full conditional.
Okay, just at the beginning when you say that, you understand that this was an implication that they were independent, but actually it's because you assumed they were independent.
It's because, yes, it's absolutely because I assume that they're independent in the model, in the prior structure, yes. Okay. Yep. Okay, so now the last one we need is the full conditional for beta. So we do the same thing, write down the full conditional for beta as proportional to the target distribution. Do the same thing where we drop every term that does not involve a beta. And there again, the product should go up to capital K. All right, and so now we can simplify this a bit. And see, I have n's all over the place on this slide. Right, on this slide, n's are equal to k's. Okay, capital K's, not little k's. All right, so if these are capital K here, what does this look like? So I feel people are a little bit hesitant, but they seem to be on the right answer. What are you thinking? Louder this time? It's a gamma, truncated, right? So absolutely, if we don't have this indicator function here, then this is a kernel of a gamma. Right? So this now is a truncated gamma. Right? And we'll talk about how to deal with that in a second. We can actually sample directly from this guy using the inverse CDF method. Okay, so this now is starting at least to define our Markov chain Monte Carlo algorithm. We're going to sample from each of the theta k's from their full conditional. We're going to sample from alpha given its full conditional, but this is going to be a Metropolis-Hastings step. We're going to sample from beta in its full conditional, but this is going to be an inverse CDF method step. Okay? And we're going to go through the details of that in a second. But before we get there, I want to talk about this idea about conditional independence and the use of graphical models to understand where things are conditionally independent. Oh, I didn't actually write down. There's the gamma distribution that we're interested in, again with n replaced with capital K. Truncated gamma. All right. So here is a graphical model. For simplicity now, I'm just thinking about two counties. All right? So this is just a graphical representation of the model that I wrote down. All right? So the data that we observed in that county depends on the number of person years in the county, n, and the expected death rate, theta. Right? If we knew these two things, then we would know the probability mass function for the number of deaths that we observed. Right? The expected death rate in the county 1 here depends on, in the prior, on alpha and beta. Right? That's the arrows from alpha and beta to theta 1 and from alpha and beta to theta 2. And we have the same thing over here for county 2. Right? So this is just showing the structure of this hierarchical model as a graph. Who's seen graphs like this before? Yeah, I was expecting not many people. All right, does that at least make sense what's being depicted on the graph? So the data, the distribution for data for the number of deaths depends on the number of person years and the expected death rate. The expected death rate depends in the prior on these parameters alpha and beta. Okay. All right, so this is fine for two counties. Right? It would be pretty unreasonable to write this out for capital K counties, where in our example that's 3,055. Right? So we're going to use a shorthand notation of this plate, and sometimes you might see this plate as being replicated. Right? So this rectangle might look like, might be sort of three-dimensional looking. Right? But the idea is that this is going to be repeated for every county. All right, so for every county, the number of deaths depends on the number of person years times the expected death rate. The expected death rate depends on alpha and beta. So far, so good? And this now is only because we have assumed independence in the prior for our expected death rate theta. Right? If not, then on this slide, there'd be an arrow between theta 1 and theta 2, because theta 1 and theta 2 would depend on each other if they weren't independent. But we've assumed that they're independent. So we have this structure. And without getting too much into graphical model theory, of which there's a huge literature, there's two relationships about conditional independence that I want to point out. All right, so this is the DAG there stands for directed acyclic graph. These are the types of models that can be fit using bugs and JAGs, or those that can be represented as a directed acyclic graph. Directed just means that the arrows here, that there are arrows and not just edges. Right? So there's actually a directionality in the graph. And the acyclic means that you can't start at any node and return to that node following the arrows. Right? So hierarchical models can be represented as directed acyclic graphs. And the first relationship is that any node conditional on its parents is conditionally independent of all other nodes except its descendants. Right? So the idea here is that you're going to actually be able to read off of this graph notions of conditional independence. Right? So the idea here is that in this particular graph, let's look at theta k. Right? So theta k's parents, I guess I haven't defined parents for you, and this is where I was trying not to get too much into the graphical model theory. But the parents here are the ones that have arrows leading into that node. So the parents of theta k are alpha and beta. Okay? And this relationship says that this node is conditionally independent of all other nodes in the graph. What you should be thinking right now is theta 1, theta 2, theta 3, theta 4, right? All the other thetas and the other data for that matter. Right? So it's conditionally independent of all those nodes, conditional on its parents. The only nodes that it's not independent of are anything that's a descendant of that node. Any arrows coming out of that node, it's not independent of. All right, so in our model, right, we've already shown mathematically, but now from the graph, we should have been able to understand that the full conditional for theta k, right, here we conditioned explicitly on all of the data and all the other expected death rates and alpha and beta, right, only depends on the data for that county and alpha and beta by this rule right here. Yes?
So this ignores spatial correlation, for example, and it's applied to this case.
Yes. Well, I've ignored spatial correlation in the construction of the model. Right? So I've built a hierarchical model for these data, and I absolutely agree that a spatial model would be better for these data, but we're not going to get to that in this class.
Okay.
Yes?
But I thought there was an assumption on the model before that the theta k's are independent. Isn't that?
Yes. So that's written in this model. So the theta k's, right, conditional on alpha and beta, are independent in the prior. Right? And that's why there's no arrow from this theta k to any other theta k. Right? If this theta k depended on any of the other theta k's, there'd be an arrow going from that theta k to this theta k. Right? Like an arrow from theta 1 to theta k. But there isn't. Right? In this graph, there's no arrow there. Yes?
Is this equivalent to saying there's no bidirectional arrows to the node, or to and from the node?
Is...
Because what I'm hearing is conditional on all the arrows pointing to a node is conditionally independent of nodes except for all the arrows pointing out of the node. So therefore, it's saying that there's no arrows that point both in and out.
Okay. So let's just be clear. So what you repeated, which was that a node, given all the arrows pointing into that node, is conditionally independent of all other nodes except for the arrows pointing out of that node. Yep. I just want to reiterate what you had said. So yes, so that is absolutely true, right? That's equivalently to saying what I said there. Now your question was about whether that means that there's no arrows pointing into the node.
Well, my question.
Or pointing.
The only thing else that I can imagine is that there could have been arrows that pointed that, or there could have been edges that were both directed into and out of the node, the same edge. Right? Is there any other type of object that connects to the node except for arrows pointing in, pointing out, and arrows that point both directions?
So let me just. So I believe that in the construction of hierarchical models, you're not going to have the situation you talk about, where there's arrows pointing. So I don't, there are arrows pointing into this node and arrows pointing out of this node, and so.
But I guess I'm trying to figure out what is actually being asserted by the bullet point. I mean, because it basically says if you condition on all the arrows, it's taking the whole universe of arrows pointing in and arrows pointing out and saying we're independent except when we consider them.
So I mean, so yes, that's absolutely what it's saying. Did you have?
I was going to try to clarify.
Yeah, go for it.
But I mean, I feel like anything pointing in would be apparent, right? There's nothing that says we need more. There's nothing that says we have to have precisely two parents to any given node, right?
Right. Yeah.
It's more or less what I was going to say. He said that also we can't have an arrow pointing both in and out because.
Then it'd be a cycle.
Yeah, that'd be a cycle.
Right. So yeah, we couldn't have an arrow pointing from theta k back to beta, because that would be a cycle. So these are statements about this particular graphical structure. But so here's the nice thing. The idea here is that imagine now a much bigger hierarchical model, right? So that we have theta k to the lambda k to the psi k, whatever, right? Now if we have, so theta k went to lambda k, let's say. Now lambda k, given theta k, is conditionally independent of alpha and beta, for instance. Right, so this is, a more general statement than just this particular model that's here, but we're just applying it to this model. All right, so the question then is, what can we say about alpha and beta? And it gets really now too deep into graphical model theory, but all I wanted to say is that generally, what I'm calling here top-level parents, so the alpha and the beta, are not going to be conditionally independent of other things. Right? They're not going to be conditionally independent. There's nothing that there's no parents that we can condition on, right, to make this first bullet point have any effect. Right? So the idea here is that, again, I'm not getting too much into the details here, but that alpha and beta are not going to be independent of each other, conditional on anything, even conditional on the theta k. Right? You might think, given this model, if you knew the theta k, that alpha would be independent of beta. But we just saw on the previous slide it's not. Right? When we derive this full conditional here, the full conditional for alpha depends on beta, and the full conditional for beta depends on alpha. Okay. So mainly the point here is when you're thinking about the top-level parents there, right, yeah, they're not going to be conditionally independent. Generally, sometimes you can get them to be independent. And there is a whole graphical model theory about when they would be independent. All right. If you go and look at the examples for bugs and for, I don't know if JAGS has the same kind of user manual, but for sure for bugs, they'll show you the graphical model for all the models that they fit. Like there's a whole set of examples for using bugs. And you can go and look at the graphical model. But the whole idea here was just to give a bit of intuition behind the conditional independence that we actually observed. Right? That is, the expected death rate in each county is conditionally independent of all the other counties given the alpha, beta, and the data for that county. Yes?
But, I still don't get it. You say that conditional on its parents and all these conditional independent of all other nodes except the descendant. But isn't that an assumption? You're assuming that is true. Or is that always true for every model?
So this relationship that the full conditional is conditionally independent, is a result of the assumptions we have in the construction of the model.
Yes.
Right. But it's not that we're assuming this right here. Right? It's not that we're assuming that the full conditional is conditionally independent. It's that it results out of the hierarchical structure that we put into the model.
And that is only because we're assuming. Okay, that's only an assumption, a direct assumption, isn't it? Or is an implication?
No, this is an implication. This full conditional being conditionally independent is derives from the fact that we made way the heck back here, right? Because we made these assumptions.
Okay, it's only necessary that the theta k's are independent. Is that the only thing we need?
Yes, that the theta k's are independent. Exactly. That the data are independent too. Yeah. So, I mean, you can imagine trying to write down different models of this sort, right, for different models that we have, for different assumptions that you make in the model. And then you can see what effect that they would have on this result. Okay. All right, so I mentioned before that for alpha, to sample alpha, we don't know the full conditional distribution, and so we're going to use a random walk metropolis. So the idea here is that, so notice here also that alpha is conditionally independent of y, given the thetas. Right? Notice that this full conditional distribution has no y's in it whatsoever. It only involves thetas. All right, so this is our target distribution in our random walk metropolis. Here's our proposal, where we're going to center on the current value and get some random jitter around that value. And what we need to do then for random walk metropolis is to derive the acceptance probability. So here's the acceptance probability. Because this random walk is symmetric, So this is a well, most random walks you construct are symmetric. Otherwise, it's not quite so random. Anyway, so it's a symmetric proposal distribution. So in the Metropolis-Hastings acceptance probability, that ratio of proposals just cancels. And all we're left with here is a ratio for the target distribution under the proposed value, alpha star, and the current value, alpha j. Yes? Yeah, so so the question here is about where the proposal distribution comes from, what should you use. Normal is probably by far the most common thing to do. But there's no reason. You could use a uniform, you could use a T, you could use lots of different things. It's convenient to use ones that are symmetric, right? Because then in the acceptance probability calculation, that proposal part cancels. All right, so there's not really much we can do here, right? It's simplified just slightly. But basically what you do is you calculate this probability, or this ratio right here, and you accept the new value with that probability. If it's larger than 1, then you would always accept. Right? Notice here that there's nothing in this proposal distribution that keeps the values for alpha between 0 and a naught. So that proposal distribution can propose values that are outside that range, but then this indicator function here is going to set it to 0. Like the probability is going to be 0 for any value that ends up being outside that range. And notice then that means that I didn't put the indicator function that's in the denominator in here. Right? There should be an indicator function in the denominator, but we had that value has to be between 0 and a naught. Otherwise, we'd have a result that's undefined. And what that really means is that the initial value that you choose must be between 0 and a naught. Right? You can't start this thing out at a value that's not in the right range. That's not a valid draw from the prior, for instance. All right, so this is all we do for random walk. Right? We propose a value. We accept it with the probability that's the minimum of 1 and this. And if not, then we set alpha j plus 1 to alpha j, the previous value. And we just move along.
Could you say again what alpha star is?
Yeah, alpha star is just a draw from this proposal.
Okay.
So alpha star is a draw from a normal alpha j, sigma squared.
Okay, and so then the alpha j that's in that equation is just it's always the initial j, or?
The previous iteration's j.
Okay.
Right. This a to the 0 is the initial. Okay. So one question then is, well, what the heck do we set sigma squared to? Right. We have to set that value to something. Right. There we go. Sigma squared is a tuning parameter, so you have the choice as the expert here to set sigma squared. And so we're going to talk about how we should set that. So here's a little demonstration for 2 examples here. In this example, the target distribution is the black line. It's just a standard normal. And now I'm considering 2 different proposal distributions, both centered at the previous value. And with mean, we're pretending here at this point that the previous value is 1. And sigma, so the standard deviation, on the first proposal is 0.1. On the second proposal, it's 10. Right, so here's 2 sort of extreme examples. And just to give you a sense for what happens. So on the left side here and on the bottom left is the trace plot. So this is the actual draws versus the iteration number. Right, remember here that the target is a standard normal distribution. Right, so what you'd like to see is 95% of the values between -2 and 2, right? You want to see this random walk metropolis just freely flowing between -2 and 2. When the tuning parameter is too small, what happens is that you basically always accept, because you're always proposing values right around what the previous value was. And so when you calculate the acceptance ratio is about 1, because that value is not very far away. So you always accept. That sounds great, right? Metropolis-Hastings, you always accept. Except the problem is that you don't traverse the whole across the whole target distribution, right? Remember, this is a standard normal. But we've only gotten values basically between 0 and 1. In contrast, now we have a huge variance in our proposal distribution, right, to the point where the red line here, which is the density for that proposal distribution, it's centered at 1, it looks almost uniform, right? It looks extremely flat. Right, so the problem with this proposal is you're going to propose lots of values that are really far away from the target distribution. Right? And what happens then if you propose values that are really far away is that you get stuck. The chain doesn't move here between iterations 1 and 11. It doesn't move again between iterations 35 to 50, basically. Right? All those spots where it's flat are spots where the proposed values were so unlikely that you never accepted them. Okay. So the point here is that hopefully it's clear that there should be some middle ground here. Right? You don't want the proposal, the tuning parameter to be too small, because then you don't traverse the whole target distribution. You don't want it to be too big, because then you rarely move. Okay? All right, so it turns out that, at least in the class of normal target distributions, that you can show that there's an optimal acceptance rate that's about 0.44 in 1 dimension. So this is a 1-dimensional target distribution, just a standard normal. It moves down to about 0.23 for larger dimensions. So the idea here is that what you want to do is you want to choose your tuning parameter so that it attains or gets close to this optimal acceptance rate. Right? So what you do is you run your Metropolis-Hastings for a while. You run the whole Gibbs sampler for a while, see how often you accept. And if you accept too often, then you make the tuning parameter bigger. If you don't accept often enough, then you make it a little bit smaller. Okay. See, there's another typo. This is when I was doing copy and replace with all my I's to K's. All right, so the idea here is we're going to talk about burn-in in a second, but you're going to change the tuning parameter during burn-in, and then after burn-in, you're going to just fix it. At least that's sort of the easiest approach. There are other approaches you could take, but. Okay, so, all right, so here's the sampling for beta. So if we want to sample for beta, we've already commented before. Now I actually have the right values here with the capital K's. This is a truncated gamma. And so we're going to use the inverse CDF method. And then basically the idea is we're going to find the quantile under this gamma that's associated with B naught. Right, so find the quantile here that's associated with B naught. And then sample uniform from that restricted range. And now use the inverse CDF of F on that U to get a sample, the next sample for beta. I will post the code that I use for this so you guys can see what's going on in the code, but that's the idea. Right. So this now is an exact draw. So right, this is a Gibbs step because we've actually sampled from this distribution right here. So the only non-Gibbs step we have is alpha. All right, so here's sort of the full algorithm. And I want to make explicit here that the first sample we get is actually a joint sample from all of the thetas. That's the first step. Right? Because they're conditionally independent given the alpha and betas, we can actually draw them all jointly. But to draw them all jointly, we actually just do it individually. Right? But this is actually a joint draw from the entire theta vector because they're conditionally independent. Right? We could have equivalently shown mathematically that this distribution right here factors as the product over K of all the different posteriors, all the different gamma distributions for the theta case. All right, so we sample the whole vector for theta. The key here is that we're using the previous value for alpha and beta to get the new value for theta. Now we've got a new value for theta. That should be beta to the j. So we've got a new value for theta, and we're still using the old value for beta to get a new value for alpha. Right? This is again a Metropolis-Hastings step, and so there's a chance that we didn't actually move. Right? And then we draw a new sample for beta, given the new value for alpha and the new value for theta. Yep.
Should the 3 should both be J plus 1 and the alpha and beta?
Yep, J plus 1s too. Yeah, see, that happens to me all the time. First time around, lots of typos. Yes, so just to be clear, in steps 2 and 3, this should be alpha to the J plus 1 is being sampled from its full conditional, and beta J plus 1 sampled from its full conditional. Thanks. Yes. All right, so this right here is what we call a Markov chain Monte Carlo approach. Right, so any sort of combination of these Metropolis-Gibbs, there's other options like slice sampling and so forth. Right, all of those approaches collectively are called Markov chain Monte Carlo. All right, by construction here, the stationary distribution of this Markov chain is the target distribution that we're interested in. Right, because we've decomposed this as a bunch of Gibbs steps and Metropolis where needed, the target distribution is, the stationary distribution is the target distribution that we're interested in. Right, and so we know that this vector of draws, as j goes to infinity, becomes a draw from the target distribution of interest. All right, so, yes. All right, so this is a key point, which is why I put it in red. We absolutely never know if we've actually reached convergence in our Markov chain. Right? I'm going to now talk about methods that we have to tell you if you have certainly not converged. But even if those methods tell you that, well, they don't indicate that you have not converged, that doesn't mean that you have converged. Right? Right, so we can never know, we can know if we have not. All right, so I favor the approach, as does Gelman, of using multiple chains at dispersed starting points. That should really be dispersed relative to the posterior distribution, which of course you don't know, because that's the whole reason you're doing this. All right, so I like trace plots just for intuitively understanding what's going on. When you get to harder and harder problems, it becomes less informative to actually look at trace plots. In particular, in this example, we have 3,057 parameters. Right? It seems a bit arduous to look at that many trace plots. Trace plots, again, are just the parameter value versus the iteration number. Okay. Oh, I guess I said it there. I do like the Gelman-Rubin potential scale reduction factor. This should have a factor. N here is the number of iterations. B is the between chain variability, and W is the within chain variability. If everything is working fine, you would expect the between and within chain to be about the same. So then when you divide by n here, you get something that's approximately 1. All right, so those are my two favorite approaches. There are other approaches, in particular approaches based on really long chains. So I want to give, here's a trace plot and some intuition in terms of what's going on. So in this case, the target distribution is a standard normal, and we started with a value of 10. Right? And so we're going to run this Gibbs sampler in this case. Yeah, all right, so what it seems clear is that we have not converged here. Right? Early on, we have not converged. We're sort of getting somewhere. And then we get down to here, and then sort of maybe things steady out at this point. Right? Maybe. All right, so what we do typically then is that we pick at some point to stop the chain, and we call everything that happened before, in this case time point or iteration 500, we call this burn-in. And everything after that time point is what we actually use to perform inference. Right? And the reason is this. So imagine calculating the mean of this sequence of points up to each iteration. Right? So you're trying to estimate the mean of this standard normal, which we know is 0. Trying to estimate the mean, and you can do that sequentially at each iteration by taking the mean of all the samples before that iteration. That's this red line. Right? So what we see here is even at a time point 1,000, you have some bias associated with the fact that you started up here at 10. If you drop all the burn-in iterations and just use those post-burn-in, this is what you get. Right? So you get some wobbliness here, but it's sort of centered around the true value. right? This is after now only 500 iterations, right? Because we've only used the post-burn-in iterations. This is using all the iterations, but it's biased because of where we started. All right, so what we typically do is we run it for a while, and then we trash all the points, all the iterations before we think that we've converged. Yes?
What does JAGS do as far as cutting out the burn-in?
Right, so JAGS, I guess we're out of time here, so I'm probably going to finish up on Thursday. JAGS, in the JAGS.model step, that's when it's doing this burn-in part. And then after that, when you do the coda.samples or JAGS.samples, then that's what you're using for inference.